Okay, good afternoon, everyone. My name is Anastasia Ryazanova, and I'm a coordinator of the research infrastructure. And today I have a great pleasure to welcome you to the new webinar series that are organized together with MAX4. And the topic of today's webinars will be dedicated to the ForMAX beamline. And it's my great pleasure to welcome Samuel MacDonald and Kim Nygård from MAX4, who will present to you the general overview of the ForMAX beamline. Please, the floor is yours, Sam.
Thank you very much for the introduction. Good afternoon, everyone. Welcome to this research webinar. Yeah, so in this talk, I will introduce briefly the MAX4 laboratory. What it is, how it works, and then focus on the ForMAX beamline and the instrument itself, showing the experimental techniques of the beamline, including some examples of the kinds of measurements that can and will be able to be performed at the beamline. And I'll also take you through the setup of the instrument, and show some details of the sample stages, detectors that we'll have to give you all some ideas of the types of experiments that you'll be able to do. So this is MAX4. So it's a state-of-the-art synchrotron X-ray laboratory which provides experimental techniques for research in materials and life sciences, funded by the Swedish Research Council, Vinnova, Knut and Alice Wallenberg Foundation, Region Skåne, and then 12 Swedish research universities. So it's very much a versatile X-ray microscope, and we provide access to 16 beamlines currently, which offer a range of techniques in X-ray spectroscopy, scattering and diffraction, and imaging. And it's open to external researchers worldwide, from academia, research institutes, and industry. So yeah, as I mentioned, there are three main research areas: imaging, diffraction, scattering, and spectroscopy, and by which beamlines are grouped, related to the specific X-ray techniques that are performed and offered at the individual beamlines. Just highlighting a few of these techniques. For example, for imaging, we have, for example, X-ray tomography, which gives non-destructive 3D characterization of the internal structure of a sample at the microscale. And then we have scanning transmission X-ray microscopy, for chemical elemental mapping of thin samples at the nanoscale, and coherent diffraction imaging and ptychography for imaging structure at the nanoscale, also in 3 dimensions. Examples for diffraction and scattering: we have powder X-ray diffraction for studying atomic structure of crystalline materials, small angle X-ray scattering for quantifying nanoscale differences in density in a sample, and things like X-ray photon correlation spectroscopy, which can provide information about the dynamic properties of the material. And thirdly, we have spectroscopy. For example, X-ray photoelectron spectroscopy and X-ray fluorescence for analyzing surface chemistry and elemental composition of a material and the chemical and electronic states, for example. So yeah, so MAX4 is very much a versatile X-ray microscope with high energy light source and intense X-ray beam that allows us to probe down to the atomic and molecular level within a sample or material. And then these are just some of the main techniques that are provided. And of course, the MAX4 website gives very much detailed information about each of the beamlines and the techniques that are provided. So how does MAX4 work? Just briefly. So this shows a picture of the facility. Electrons are produced from an electron gun and then accelerated to a speed close to the speed of light as they travel along the linear accelerator or the LINAC, where the energy of the electrons increases. The accelerated electrons are then circulated into two storage rings, depending on the energy, a lower 1.5 GeV ring or higher 3 GeV ring. And then magnets producing strong electromagnetic fields are used to deviate or bend the electrons as they travel around the ring. And then this releases energy in the form of synchrotron light, which is then directed into the different beamlines as shown here in blue. And then each beamline uses this X-ray beam to probe a sample or material in specific ways, depending on the technique being employed. So this just shows a map of the different beamlines currently operating or in commissioning phase. Just taking a few examples. We have NanoMax, which uses a nanofocus beam for fine local mapping with scanning XRD imaging and coherent diffraction imaging and typography. Another example, SoftDMax for soft X-ray investigation of nanoscale structure and elemental mapping of thin samples using scanning transmission X-ray microscopy. Another example is DanMax, combining powder diffraction with full field imaging and tomography. COSAX doing small angle X-ray scattering. And then, of course, we have ForMAX, which is on here, where we combine small and wide angle X-ray scattering with full field imaging and tomography. So now let's focus now on the ForMAX beamline. So there's a strong need and drive from the forest industry in Sweden to develop new and more efficient usage of their renewable bio-based raw materials. And to promote research on new and novel materials and specialty chemicals from forest raw material. Through the Tree Search research platform, the forest industry is funding the beamline at MAX4. And this has the objectives to foster research collaborations between academia and industry, and to provide academic and industrial users with access to advanced materials characterization tools, which MAX4 can offer. So this has led to the ForMAX beamline at MAX4, where the Wallenberg Foundation has funded the costs for construction, And then industrial members of tree search fund operation costs. And then with this investment, 50% of the beam time at ForMAX will be reserved for tree search members. And then part of that time can be exchanged for time at other beamlines at Max4 also. And then the other 50% is allocated in open calls for experiments. And then there's general non-proprietary access. So just to give you an idea of the current status of the beamline, before we go into the techniques and setup. This shows a sort of a rough timeline. So we had procurement and manufacturing of the optical components, such as monochromators, focusing mirrors, that began in 2019. And then these were installed in 2021, allowing us to take first light in early 2022, which was an exciting time. And then we're still doing some final installations of the end station in the experimental hutch, but about 4 months ago, we had beam for the first time in the experimental hutch. And then just before the summer break, we had the first test experiment. So you can see this image on the right here, measuring scattering from a piece of oak. So it's nice to show our first measurement at the beamline. And then we continue with commissioning through the rest of this year, with commissioning experiments into early next year, and then go into regular user operation around February, March next year. So, what can we do with the ForMAX beamline? So many materials exist which exhibit structural hierarchy. That is, that they have important structure at many different length scales. So taking wood, there's of course there's one such example of a hierarchical material. A fiber composite material consisting of the fiber network and the cellular structure at the microscopic scale, through the ordered assemblies, the fibril matrix structure that make up the cell walls, and they're at the sort of the nanoscopic scale, and then down to the cellulose, which forms the sort of the crystalline building blocks that are the fibrils at the macromolecular scale. So yeah, very much a challenge related to such hierarchical materials is to improve understanding of the structure function relationship across these different length scales. This is important, of course, from the point of view of developing new material concepts from, for example, forest raw material, with improved properties or even new functionality. And yeah, to address this challenge, the ForMAX beamline will allow multi-scale structural characterization of current, new, and advanced materials, and with temporal resolution to study materials processes in situ, which is very much an important part. So yeah, ForMAX is a flexible instrument combining two principal techniques. Full field tomographic imaging, where you get to, as I mentioned earlier, you get a 3D image, a virtual 3D image of your sample, which you can then characterize the internal structure with a spatial resolution of down to around 1 micron. And then combine this with small and wide angle X-ray scattering, which gives us our nanoscopic information. And then we can combine these two techniques with scattering as the contrast signal using sort of scanning SAXWAX imaging. And then together these techniques cover a wide range in terms of spatial resolution for the nanometer to millimeter length scales that are important to study. The techniques are widely applicable to different materials and fairly insensitive to sample environments. So yeah, again, important part is that we'll be able to look at materials processes in situ, whether it be humidity or applied temperature or mechanical load, for example. So yeah, just showing sort of our different length scales here in the picture at the bottom. So full field tomography will allow both absorption, contrast, and propagation-based phase contrast imaging. So I mentioned covering length scales from a few millimeters down to 1 micron, sorry. And in the context of our wood sample, we're in this regime, so enabling the cellular structure of the fiber network and the cell walls to be imaged in 3D. And then the size, shape, and orientation of the fibrils, for example, at the level of the fibril matrix structure, can be probed using small and wide angle X-ray scattering at length scales from several nanometers to several hundreds of nanometers. So that sort of gives a bit of the background of what ForMAX will be able to do in terms of these hierarchical materials. I'll spend a bit of time now looking at how these two techniques work with a few examples, just to give you an idea of what can be performed. So X-ray tomography, how does it work? So this shows the basic setup for X-ray tomography acquisition. So X-rays are attenuated by the sample, and then we measure an X-ray projection or a radiograph of the transmitted intensity on the detector. So this shows an example of a projection. This sample is actually a fiber reinforced polymer composite. And then the sample is placed on a rotation stage. And then whilst the sample is rotated in the X-ray beam, many projections are collected over a range of either 180 or 360 degrees. Yep, so we rotate the sample and then we collect many projections over 180 degrees. And then the sample is then computationally reconstructed from these projections to give a stack of 2D slices. So we'll show one here so this is a horizontal slice through the sample. And then if I just zoom into a small section, you can see in the slice the location of these small fibers in the sample. We can then visualize this in a 3D volume, which can be then used for quantitative analysis. So just a simple example here, this composite was subjected to a tensile load to quantify the progression of fiber cracks as a function of the applied load. So we can see on the right-hand side in red these small cracks that have developed as the applied load is as the load is applied, and then we can watch their formation and their propagation, and how the morphology interacts with has an effect on the progression of these cracks. So in standard absorption tomography, the contrast between different components within the sample arises from the difference between the linear attenuation coefficients. So consequently, for materials with low attenuation, and which contain components with very similar attenuation, this can result in poor contrast in terms of being able to do any quantitative analysis of your structure. In this case, phase contrast can be significant and much more, the phase shift can be significant and much more sensitive. So synchrotron X-ray sources such as MAX4 allow us to take advantage of propagation-based phase contrast imaging. So here shows a projection, again, of a different polymer composite. It's an epoxy matrix with some capsules inside containing a solvent. If I go one slide, as we increase the sample to detector distance, or the propagation distance, you can see that the boundaries of these capsules within the matrix are enhanced. So that's just showing this Fresnel effect of this propagation-based phase contrast. And then applying, again, computationally in reconstruction, a phase retrieval filter. This results in increased contrast. So here I show the same 2D slice with no phase retrieval and with phase retrieval. So you can see we can now see these the capsules and their contents inside, and able to quantitatively characterize the structure. So the enhancement of the difference in grayscale intensity between the matrix and the contents of the capsules, as I say, facilitates their segmentation for quantitative analysis. So I just take a line profile across one of the capsules. You can see with no phase retrieval, the grayscale intensity is pretty much level, but with our phase retrieval, we can the difference is much more distinct. Yeah, and this, as I say, enables us then to go on and do some characterization. In this experiment, we did a crack growth study. So these capsules actually promote healing of cracks. So in the top left, in yellow, we show that these are the filled capsules. So the matrix has been made transparent, so we just see the capsules themselves. And we grow a crack, shown here in red, in 2 crack growth steps here. So the crack grows further in the second step. And you can see the capsules that have emptied their contents in grey yeah, they've emptied their contents into the crack plane. So you can just see here the healed crack with the contents of the capsules that have filled into the crack. And then some catalyst in the matrix causes some polymerization and effectively heals the crack. So this would have been very difficult without using phase contrast imaging to be able to study what's happening as we grow the crack in this case. So just an example of how that helps. Another example, there are many cases where one would like to follow an in-situ process with high temporal resolution. So this example shows fluid flow through a porous glass bead pack, sort of using as a model sample to mimic rock structures. So it's just an example of high-speed tomography, because in such a case, one would need to reduce the total exposure time for a tomography acquisition, ideally to around 1 second, for example. For higher temporal resolution, one can use, sort of high-speed cameras, for example, going to kilohertz frame rates. But also in parallel, you can reduce the numbers of projections for a scan, as shown here. For example, taking an initial scan, which is shown on the left, with a high number of projections, for example, 1500 projections around your 180 degrees, to preserve resolution. And then subsequent scans during the actual flow process, we can take with reduced projections, because for that, we're just really interested in the fluid. So we still see the structure. So this is comparing two different projection acquisitions. You can still see the structure, but yeah, we can use our initial scan for the high resolution. And again, this shows one with 1500 projections compared to 180. Again, the structure is still sufficient for what we need for the experiment. And then we can, I should just highlight that doing this, we could then reduce the time between tomography frames to below 2 seconds. And now, yeah, you can go to 1 second or even faster. So yeah, just to quickly show, we were looking at how the fluid flows through this structure. So this is showing sequential tomography frames. So as mentioned previously, tomography measures the intensity of the transmitted beam as X-rays are attenuated by the sample. If we move on to small and wide angle X-ray scattering, the beam is transmitted through the sample, and intensities of scattered X-rays are measured and collected on the detector as a function of the scattering angle 2 theta. So with subsequent data reduction, such as radial integration, we can extract profiles of intensity as a function of the scattering vector, for example. And then, yeah, you can extract information about the position, width, and intensities of the peaks, providing structural information about nanoscale features within the sample. Yeah, size, shape, and orientation. Just to show one example of the use of SACs shown here. This was a group from the chemistry department here in Lund looking at dissolution of cellulose in alcoholic solutions. So obtaining SACs profiles for different concentrations of microcrystalline cellulose solutions, and then they could determine the stability phase diagram of microcrystalline cellulose in these solvents, revealing different regimes where solutions are stable, metastable, or unstable. But yeah, in general, for sax wax, nanoscopic characterization, length scales, sort of 1 to 500 nanometers, and then time scales down to a few milliseconds. One can take this, take such scattering experiments a bit further by using scanning sax imaging with a small beam, for example, down to a few microns. You can take this, scan the sample through the beam, and at every position, take a scattering image. So yeah, the sample is translated in the vertical and perpendicular directions. And then you can map how the nanoscopic structure varies through the sample. It could be, for example, orientation of some fibrils within the sample, for example. And just very briefly to show, and one example, looking at injection molded polymers, thesis from Nia Bjorn, and how the hierarchical structure morphology varies across a sample, and link that to processing conditions, for example. But yeah, in general, for scanning sax wax imaging, nano and microscopic characterization with length scales from nanometer to millimeter, beam size down to 1 micron, and time scales, yeah, from seconds to hours, depending on the sample that you're scanning. So let's now have a look at the ForMAX instrument itself and how we'll go about performing and combining these two techniques. So just initially, this shows a simple schematic layout of the ForMAX beamline. So energy range 8 to 25 keV. We'll have 2 monochromators, yeah, sort of for high flux, and then for higher energy resolution. Focusing mirrors to focus the beam, and then roughly beam sizes at the sample nominally will be around 10 micron up to 1 millimeter. But we will be employing some lenses which will be able to focus, do micro focusing down to 1 micron, and also some to expand the beam for tomography experiments up to around 5 millimeters, roughly. So this shows the layout of the experimental hooks at the beamline. So starting at the upstream wall, we'll have 2 beam conditioning units consisting, for example, filters for specific attenuation of the beam as and when required, fast shutter to protect the sample from unnecessary exposure to the beam when it's not needed, considering sort of radiation damage and so forth, slits for collimation of the beam to minimize background scattering, and then, as I mentioned, yeah, two sets of lenses for microfocusing and beam expansion. And then we have our sample table and detector gantry for mounting sample table for mounting our sample stages, and then detectors on the gantry. And then immediately downstream of that is our flight tube, 9-meter long evacuated flight tube for small angle X-ray scattering. Showing in a bit more detail the end station. So the sample table will have vertical, lateral and pitch motions for positioning sample stages, which will be mounted on top. Both the tomography microscope and the wax detector will be mounted on this motorized gantry, which will allow the movement in and out of the beam path, depending on the required setup for the experiment. And importantly, this will allow combined tomography and SAX-wax experiments to be performed in a sequential mode. And then the SAX flight tube houses the SAX detector on a trolley, enabling the sample to detector distance to be varied between approximately 0.5 meter and 7.5 meters, something like that. So just to briefly show you, give you an idea of the sample stages we'll have available to give you a feel for the environment around. It shows a stack of the sample stages for the tomography setup, and its real focus on modularity and flexibility, so that stages can be easily added, removed, dictated by the experiment. So we'll have starting at the bottom, a linear stage for movement along the beam, allowing us to sort of alter the propagation distance for phase contrast, as I was talking about earlier. A vertical stage for additional movement, additional vertical movement, in addition to the sample table, and for potentially performing sort of helical tomography measurements. We'll have a rotary union, which allows passage of fluids such as gases, liquids, dispersions, for example, through the rotary axes, so to connect to sample environments mounted on top. An electrical slip ring to pass through power and electrical control signals from the stages and the from the stages and the sample environments mounted on top of the rotary stage. And then our rotation stage will be an air-bearing one with speeds up to around 700 RPM, with a load capacity of around 40 kilograms, slightly higher. And then we'll have sample alignment on top of the rotation stage. And as I said, it's very flexible and modular in that we can remove stages. So a common setup might just be the rotation stage and the sample alignment stage on top, which gives, of course, much more space for sample environments to be mounted. So yeah, just to confirm, focus on modularity and flexibility, propagation-based phase contrast, rotation stage enabling temporal resolution of, say, 1 second or even better, and then the ability to incorporate sample environments. For smaller sample environments, these can be placed on the sample alignment stage, but for heavier ones, we can place them directly on the rotation stage. Briefly about the detectors. This shows the setup consisting of a microscope and CMOS cameras. So your X-ray image after transmission through the sample is converted by a scintillator into visible light. Then the visible light image is magnified using some microscope optics, and then this magnified image is recorded by the CMOS camera. The microscope has a triple objective lens configuration, allowing us to easily change magnification and thus field the view size during an experiment. So this is quite nice to have. For example, one can perform an overview scan of a sample with larger field of view and then zoom in on a particular region of interest with higher resolution. Yeah, and then two CMOS cameras, both coupled to the microscope, allowing selection of either camera by switching. And these can be sort of distinguished by a higher dynamic range camera, and then at slower slower frame rates, and then higher acquisition frame rate camera with a larger double pixel size, sensor size. And then this table gives an idea of fields of view and pixel sizes for the range of objective magnifications. Yeah, as I said earlier, the nominal beam size at the sample position will be around 1 millimeter, but with lenses, this will increase up to around 5 millimeters, where sort of it's important to have a more representative sample volume in your tomography scan of your sample. Briefly, SAX-WAX stages. This shows the sample stages for performing different SAX-WAX experiments. So a modular, again, very modular 5-axis stack of stages for general SAX-WAX experiments. And then for scanning SAX-WAX imaging, you can mount 2 additional stages for pitch and rotation on top of the general stages. And as with the setup for tomography, the design is very much with flexibility in mind and ease of use, including the ability to easily install and remove individual stages for particular experiments. The detectors for SAX-WAX. So we have 2 hybrid pixel detectors. The SAX detector placed on, as mentioned earlier, on a motorized trolley inside the SAX flight tube. This will be a 4 megapixel camera with frame rates of up to 500 Hertz. And then wax detector mounted on evacuated nose cone of the flight tube. So this shows a picture down here. It has a hole in the center. So it's like a novel windmill design. A hole in the center to pass through the direct beam and also the SAX signal. And then, yeah, allowing data collection at scattering angles 2 theta from around 7 to 20 degrees. And with a frame rate of up to 1 kilohertz. So yeah, since in situ studies using materials processing are foreseen at the beamline, very much foreseen at the beamline, data acquisition times down to millisecond regime are possible. So how will the individual and combined setups for tomography and SAX-WAX work physically at the beamline? So I'll take you sort of through the setups that we'll have and configurations briefly. So the tomography setup for standard absorption contrast, where the sample is placed as close as possible to the scintillator of the microscope. And then we can increase the propagation distance for phase contrast, as shown here. So we use the linear stage upstream along the beam relative to the position of the microscope. And this also allows space for mounting sample environments, such as mechanical load devices on top of the stack of stages. And then the distance can also be increased further, depending on the sample, for example, by retracting the telescopic tube. A key feature of ForMAX is the ability to combine the two techniques in a sequential manner. So we can do this by moving the detector gantry upstream, as shown here, which then allows the microscope and the wax detector to be moved in and out of the beam path in a sequential manner. For such experiments where combining these two techniques is very much a key feature. So this is probably more clearly shown in this view. We can see both the microscope and the wax detector are in the beam path. So here's the microscope, here's the wax detector behind, with movement of the microscope in and out of the beam to do this sequential tomography sax-wax modes. So very much multimodal. The tomography configuration, gantry is moved downstream to allow the microscope to be placed in the beam path and allow the sample detector distance to be maximized, again for the phase contrast. And then for small and wide angle scattering configuration, the gantry is moved to the required position for the wax detector to be placed in the beam path, as you can see here. And then the tomography microscope is moved completely out. And then for small angle X-ray scattering configuration, the gantry is moved to its upstream position, and the microscope and wax detector are parked out of the way, and then we can allow the beam to pass through, extends the telescopic tube, and use an evacuated nose cone to minimize the beam path in air for sax measurements. So as you can see, the flexibility of the end station allows us to easily change between different configurations. So just to finish off with a couple of slides, what we think is, as I mentioned, going to be a key feature of ForMAX is multi-scale or multimodal imaging. So for example, you can first do a full field tomography scan to get a 3D image of your sample, of the full sample, and an overview of the microstructure. So I illustrate this here with a tomography scan of a polymer foam. And this overview scan can be used to define regions of interest, where it will be interesting to look with higher resolution, or at smaller length scales. So, for example, a further tomography scan can be performed on that local region of interest shown here. So as sort of taking a small region of interest from the larger scan, we can then perform on the local region of interest to look at the local structure with higher resolution, as shown at the bottom. So we sort of cover a few cells, if you like, of this foam. And then the idea would be to do local scanning, scattering-based measurements, just focusing on that smaller region to get some information on the nanoscopic structure, sizes and orientations of small nanoscopic features. So yeah, I use this this foam as an example. For example, you can also combine with in situ measurements of the changes in structure with mechanical load. So I just illustrate here. This was actually a tomography scan which was imported to do image-based modeling. So you can see as we pull the sample, you can see how the structure changes. And then also with the small region of interest. So yeah, combining the two techniques is very much a key feature of the beamline. And just to summarize again, the length and time scales for the two modes. Length scales for microscopic characterization using tomography, around 1 micron to 5 millimeters. Time scales down to 1 second. And then for scanning, wax imaging, nanoscopic and microscopic characterization with length scales nanometer to millimeter, beam size down to 1 micron, and time scales maybe seconds to hours, again, depending on the sample. Just to give a very nice illustrative example, again, of the kind of experiment that one will be able to perform at ForMAX, is to look at paperboard under tensile load. So this is from a study done here in at the 4D imaging lab at Lund University, performing an in situ tomography experiment. So at each increasing applied load step, a tomography scan was recorded. And then from the sequence of 3D images at each load step, the evolution of the strain field within the paperboard can be determined using the digital volume correlation to extract regions of, for example, strain localization with applied load. And then this can be linked to the characterization of local microstructure, sort of including fiber orientations. So yeah, you can extract the strain field, look at delamination, and then also fracture. So in performing such an experiment using a laboratory instrument, which now sort of can approach, in terms of spatial resolution, can approach what you can achieve with a synchrotron, but it would take the order of tens of minutes for a single tomogram. The added value of going to a synchrotron is that you can do a scan on the order of a second or a few seconds. So you can perform experiments, for example, under continuous loading cycle without interruption. And then for such an example, one can think about also doing multimodal imaging with scattering-based imaging. So not looking at only the microscale structure evolution, but also looking at how the fibrils are evolving or deforming over time. So yeah, just an example of the kinds of things that would be possible at ForMAX. So just to brief summary. ForMAX beamline provides multi-scale structural characterization of hierarchical materials. So that's materials with important structure at different length scales and with temporal resolution to study processes in situ. And we do this by combining scattering and imaging methods, SAX-wax, X-ray tomography, and scanning SAX-wax imaging. And the key feature, as I've mentioned, we think is multimodal imaging, so overview of 3D structure at the microscopic scale. And then local imaging of nanoscopic structure using scanning SAX-wax imaging. Just to show you the ForMAX team. So myself, Kim Nygård, scientist and beamline manager, and then we have Vahid and Joaquin, research engineers. Thank you for your time.
Thank you so much, Samuel. A really nice overview of the MAX4 and ForMAX. I was wondering if someone has questions. So you guys, if you have any, you can either raise the hand or you can post it in the chat or in the Q&A. Probably the questions will come after the second presentation. So maybe to save time, we should directly move on to the presentation of Kim. And then we will take the Q&A session afterwards.
Okay.
Yes. Thank you so much, Samuel.
Okay. I'll end.
Yes. Thank you, Sam, for a great overview of MAX4 and ForMAX. I have now the ungrateful task of going more into formalia than science and what can be done at ForMAX. So a short sort of synchron experiment from A to Z, what you need to think about. I just like to start first by mentioning the two main modes of access we have for the MAX4. The one for what we call general user access is a peer-reviewed process. So twice a year, we open a call for proposals. If you want to do an experiment at MAX4, general or ForMAX, particularly for this community, then you can submit a two-page proposal. Where you explain what you want to do, how you want to do it, and why it's important. These proposals go to, well, first they go to the beamline staff, and we just check for feasibility and nothing else. This is all MAX4 checks for. But then the proposals are sent out to external, a panel of external experts who rank the proposals based on scientific merit. And then MAX4 gets back a list for each beamline, a list with a ranking of proposals. And we start filling in the time we have available for users from the top of that ranking. Now, if you go through this route, you don't have to pay anything for the beam. It's I think quite a good deal for the users. The only thing we ask for is that if you have good results, you publish them. Now, the next proposal deadline is in 2 weeks from now, just short of 2 weeks from now, and will then cover the period from March to August next year. Now, it's maybe implicit since we have a scheme like this, and it's basically the same scheme at every synchrotron, that we will have more proposals than we can for experiments than we can award beam time to. Typically, I would say on a good beamline, this is about an overbooking factor of 2, so we can provide access for approximately half of the proposals. It's in a sense unfortunate because there are many good proposals that we can't provide beam time to. On the other hand, it ensures that the users or you think about your experiment in advance, and when you come to do the experiment, you are well prepared and work more efficiently. So as a net sum, I think it does lead to better experiments and more efficient use of the beam time. Now for the next proposal round, we will have more limited access than normally because we are still in parallel with taking users, we are still commissioning parts of the instrument, and we are also still running sort of commissioning experiments that were awarded via a call half a year ago, where experienced users come and test our instrument to ensure that it works as it should, and that it's in such a good state that that you can actually do useful research there. But from the following proposal round onwards, so in a year from now, we will be in full sort of standard user operation. The second main access mode is for proprietary access. So the time that it takes from sort of applying for beam time until you actually can do your experiment is about half a year, and this may be too long for companies who want to do experiments. So we have this faster industry tailored access, where we also then of course sign NDAs. And here the idea is you will contact you can contact our industry office, and they will have booked a few time slots in advance so that they can book in experiments on shorter notice. And you can do one-time projects, or your company can have a long-term framework agreement to facilitate access to individual experiments. If you go this route, you have to pay for the beam time. It's about 7,000 crowns per hour, but then you own your own results and you can do whatever you want with them. Most industrial users still go through the general user access mode, maybe collaborating with research groups in academia to do experiments, rather than paying for the beam time to carry them out. Okay, an ideal experiment would look pretty much like this. You have a problem you want to solve, or an idea you want to test, activities you want to test, and you think you can solve this problem or test these ideas with the help of MAX 4. You come to MAX 4, you carry out an experiment using the equipment and methods that we've developed, and you go home with an answer to a problem or new ideas. The reality is obviously a bit more difficult. You need to translate your problem into an experiment, first of all, and that usually is much easier with some experience. Second of all, you don't go home with an answer to your problem, but with a boatload of data that you need to reduce and analyze before you get the answer to the questions you posed. Now in this talk, I will focus on the three innermost pieces of the puzzle here, and give some ideas on how we try to solve some of those issues, or help you solve them. Still, I think a very general statement in the synchrotron community would be that we basically all started doing experiments at synchrotrons via collaborations, collaborating with more experienced users. I'm convinced that is by far the most efficient way of learning the tricks and trades in this business. Now, within the research community, you have opportunities for these kinds of research, a bit more formalized than normally, and we also try to help in the ways we can. So one example of how we hopefully can help you also in the future is what we call a ForMAX industry portal, and this is now for the industrial members. So we've had for a number of years now funding from the Swedish Research Council for a project headed by Alexander Matic at Chalmers to help industry make use of MAX4 and similar facilities. And the idea is, if you have a problem you think you can solve by X-rays, or in the future also neutrons at the European Spallation Source, you would come to us. There's a group of senior researchers who coordinate the activities, supervise postdocs. And the postdocs that are hired in this portal are then both method and material experts, and they can help you with all the steps of carrying out the experiment, transferring your problem into an experiment, carrying out the experiment, analyzing the data, drawing conclusions. Now the funding ends in the end of this year, but there was a new call, and we applied for continuation, and obviously hope that we can continue this portal and expand it for a number of years. Okay, so back to the second piece of the puzzle there, translating the problem into an experiment. And this is, in a sense, the most challenging piece. Now, I think it's important to highlight that that the techniques that ForMAX provide, or MAX4 in general, those should only be seen as a complement to the material characterization tools you already use. So if we have a, let's say, youngish, enthusiastic researcher here in the bottom left, who has a project, then he would probably first think of the tools, characterization tools he has in his lab. What information can I gain from those? Could expand that by using the research infrastructure that research is providing. Electron microscopy, for example. You can also do small and wide angle scattering and full field tomographic imaging using lab sources. Often those are enough. And if those are, if you're still lacking, then the next step is then to maybe do an experiment with ForMAX. And an obvious reason for going for the other techniques first is that you get access much faster. But even if you do need to go to ForMAX or Max 4, somewhere beamline Max 4, it's still useful to do those lab measurements. So this is an example of small angle scattering data on some silica particles. You don't have to care about the details. But the red and green curves are data I got from the Chalmers Material Analysis Laboratory, and these are then collected using state-of-the-art lab-based SAX instruments. And you can see for the sort of lowest green curve, this is an example that will show this sort of ringing intensity pattern in the lowest green one, which is the sort of highest quality lab data we have here. It took 10 minutes to collect such a curve, and that was after hours of optimizing the equipment. And this is then to be compared to the black curve, which was a sort of quick and dirty 1 second measurement at a synchrotron. So some of the features are there also with the lab source. Obviously, the temporal resolution is much poorer. Often also the resolution of the experiment is poorer, but you can do a lot with the lab sources. And if you, for example, need to do a time result study, it's very advantageous to do measurements or experiments first with a lab source to have some static data. It helps you plan your experiment when you know what to expect in terms of a scattering pattern, for example. Basically, the better prepared you are for your experiment, the better the outcome will be. There may also be other reasons for going to the synchrotron. All beamlines at Max 4 have dedicated sample environments. That includes also, or will include also, ForMAX. We will, for example, have a fairly unique Rio SAX setup where you can do simultaneous SAX-WAX and rheological characterization. This is not available in the current call, but we hope to open it in the next call. And there will be a webinar later, tentatively in November, by Roland Kadar about our first experiences with this instrument. Finally, Sam mentioned that we have 16 different instruments at Max 4 that can where you can do different kinds of experiments, scattering, imaging, spectroscopy on different kinds of samples. And most of these techniques are such that you won't even have them in a home lab. And through research, you will have the opportunity to also have some sort of say slightly easier access than through to these instruments than through the regular proposal on general access mode. Okay, a bit about formalia for submitting a proposal. There's actually a very good guide on the Max 4 homepage. You can see the web page here on the left. There's I think a rather clear user guide for what you need to do to get access and what to do in what order. So you can find there things like how to create what we call a duo account. So we have a digital user office, and you need to create an account there to be able to apply for beam time, and all the communication, a lot of communication will happen through there. There's also information on, or some guides on, how to write better proposals, and what you need to do to submit your proposal. The main part of the proposal is a short 2-page description of what you want to do, how you want to go about doing it, and why it is important. And you can find a template on the MAX4 homepage. But basically, it's a very short abstract, and then the main part usually is the scientific background, where you describe why it is important to carry out this experiment. If I were to give one advice, it would be keep the scientific background rather general. So these proposals will be evaluated by a handful of external experts, and they will cover a number of different techniques. They will cover. They all have their own scientific expertise, but you should not assume that any one of them has exactly working in exactly your field and has very detailed knowledge about your field. Also, they will review probably this handful of people will probably review something between 50 and 100 proposals in that review committee. So they have very limited time to read up on the research you propose to do. So I keep it very general. It should be easy to read, smooth, and it should be clear why it is important without going into too much details. The second important part of the proposal, a 2-page proposal, I think, is see the experimental methods that can also include preliminary results. And here you basically need to provide enough details that we can do a feasibility check. It often and that the review committee realizes that you are competent to carry out this experiment. If you have preliminary data, let's say you want to do a time result study and you have some static data from a lab source, from lab equipment, then that is usually advantageous to include. It shows that you know what you're looking for, and it also shows the committee that this experiment can be done at the instrument. Finally, a final say hint or opinion here on the results expected. Again, don't be shy. The reviewers will read a lot of proposals. Don't be shy about why your experiment is important, why your research is important. What this kind of proposal-based access key means is that you have to a large extent design or plan your experiment already well in advance of carrying out the experiment. It's clear you need to provide already at this stage enough details on how you will do the experiment so that it's other people can estimate if it's feasible or not. And you have to convince the panel that the experiment will be a success. This is quite difficult the first times. It takes a number of proposals before one gets a feel for the level of detail and that is required. So I would suggest, if you have an experienced colleague, go and have a chat. It often helps. Maybe that person can give some hints on how you could do something that you hadn't thought of yourself, for example. Experience usually helps in these matters. You can also contact me or Sam. It's part of our task to help you plan as good experiments as possible. I say that with the caveat of that if you send us some questions a day or two before for the deadline, then we probably will be overflooded with mails and won't be able to answer you. So the earlier you contact us, the better. And finally, I mentioned this already, but the proposal scheme can seem a bit tedious, but I'm convinced it does improve the experiments quite a lot. And in the end, this is what we want to do. We want to have successful experiments that lead to great science. Now, next week, we will have a feedback session as part of this webinar. So if you want to join, Sam and we will be there. We can give you some feedback on your ideas. If you want to join, prepare a slide or two on what you want to do and how you thought about carrying that out, and we can hopefully give you some hints. Also, other participants in that session are most welcome to give hints. I think that would be a great way for everybody to learn. Okay, briefly about research privilege access. Now, this is taken from Max4 homepage, so there's maybe a bit more text than needed, but basically, research has an agreement with Max4, and 50% of the user time at ForMAX will be reserved for research members. You will still do go through the same proposal scheme as other users. Your proposals will be sent out to the same review panel, and you will get same kind of feedback after the review panel. The only difference is in the proposal stage, you will have the possibility to tick a box that you are a research user. And if that and in that case, your proposal will then go into a different pool. So we'll have different pools for general users and research users. For the research case, we will still have the ranking by the review committee, but research then has the possibility to lift the experiments if they are deemed important for research. Now, please have a look at the user guide before you submit the proposal to ensure that that you do it correctly. For example, that the PI of the proposal has to be a research member. Okay, after the proposal review, if your proposal is accepted, then eventually we will contact you and propose dates for the experiment. And once those are settled, we will schedule it, and then you will be contacted by MAX4 to do. Then the main proposal will be contacted by MAX4 to do some formalia, create a session where you will give details on the samples you will bring, and we need that information from safety perspective. So our safety group will look into those. You also need to provide information on who will come to do the experiment and so on. But this is all described in rather detail on our web page, and it's not urgent at this point. In this stage, you can also book access to our chemistry and biolabs. So each beamline has some sort of sample preparation labs in connection with the beamline, but if you need a real chemistry lab, then we also have that on site, and you can apply for access in advance. Okay, that was a bit about translating the problem to the experiment. And then for the actual experiment, for new users, maybe the most striking thing is that we set up the experiment in what we call an experimental hutch, but we run it all remotely from what we call a control room. The reason is that we have these lethal doses of X-rays in the experimental hutch where we set up the experiment, and therefore you cannot be in that room or have the door open to that room when you run the experiment. But rather everything is demotorized and controlled remotely. So this in the picture here, we have what we call the control room of ForMAX, where you will then be running your experiment. Now this video clip here is a few months old, so it looks a bit different now, at least a bit cleaner. Further onwards, you see a meeting room where you can sit and analyze data or discuss during the experiment. And then from the control room, you have then access through this very thick lead door into the experimental hatch. Just to drop some numbers, we have, I think, more than 50 tons of lead in these walls to ensure that it's safe to be outside the experimental hatch when we run the experiment. Now the beam, X-ray beam, comes in that beam pipe, and the yellow table we have here is the experimental table where you will set up your experiment. This is still some months ago. We haven't done all the installations yet, but you at least get a sort of sneak preview of the beamline. This is our large vacuum vessel, inside of which we will have a SAX detector. I go to MAX4 every day, but almost every day, but I still think it's rather impressive looking. It sort of strikes you when you enter the hatch, and this is something unique. The ones of you with a keen eye maybe noticed that there's lots of cables there. We have about 5 kilometers of cables inside the experimental hutch just for that remote motion control that I was talking about. Okay, for the actual experiment, for each experiment, we will have a designated local contact from the beamline staff who will help you with setting up the experiment and who is also on call if you have problems. But it is the users who run the experiment. And we run experiments 24 hours a day, 6 days a week. So if you have, let's say, 3 days of beam time, it means you will have 72 hours of beam time in a row, and you'd like to use that as efficiently as possible. So it means you need to have a reasonable size of a team joining you for your experiment to be able to run those experiments efficiently day and night. I thought I'd briefly mention a few pitfalls for new users. One is radiation damage. X-rays are ionizing radiation. They break bonds, they create radicals. And in particular, if we focus the beam, then the photon density is rather high. So on the top right, I show an example of wide-angle scattering, so diffraction from cellulose. This is from a thin piece of wood. See if I can pointer, and these are diffraction, then certain diffraction peaks from cellulose. And you can see going from top left down to bottom right as a function of dose, X-ray dose on the sample, these diffraction peaks become rather big. So basically, the X-rays in this case break the crystalline structure of cellulose, and this is just unavoidable, and you just have to find means of mitigating this effect so that it doesn't affect the results of your experiment. Having shorter exposure times, minimizing the dose on the sample, if possible, cooling down, things like this. And usually it's easier the more experienced you are. The second pitfall is the data rates. That can be rather overwhelming. So if you do time-resolved full field tomographic imaging, or you do scanning saxflex imaging, you can easily collect more than 1 terabyte of data per day. I've heard of cases where they get more than 10 terabytes of data per day. And this is just an overwhelming amount of data. And it's difficult to grasp where to even begin. So again, experience helps a lot. So if you do, particularly if you plan to do a difficult experiment, it wouldn't hurt to have at least one experienced user in the group or in the team. Okay. Besides the actual experimental station, as I mentioned, we also have sample prep lab, and this is being built up then for the specific needs of you, and these are based on wishes from the user community. For example, we have environmental glove box. You can control temperature and relative humidity. when you prepare your samples, we will have two environmental chambers where you can again set temperature and control temperature and relative humidity, and you can use this, for example, for equilibration of your samples before the experiment. Okay, the final part then of this talk deals with data reduction and analysis. As I mentioned, the amount of data is overwhelming, and now if you come to us for 3 days and collect 10 terabytes of data, then there's just no way of for you to handling that. You probably don't have the resources at your university to handle it. So really the only way forward is that MAX4 is helping you with this. And MAX4 will store your data for currently we say for 6 months, but we are continuously upgrading our increasing our data storage capability, and this may be a longer period in the future. But at a minimum 6 months, we store your data so that you can analyze the data. Moreover, in the actual experiment, so at ForMAX, we aim to provide the data in a more useful reduced form. So if you look at that top left picture there, that's a diffraction pattern from wood. So it's basically diffraction from cellulose. And the director of those diffraction peaks would provide you information about the preferential orientation of the fibrils in this case. So you may use that kind of data to, for example, map out orientation of fibrils, local orientation of fibrils within your sample. And if you do that, a diffraction pattern is not a raw diffraction pattern is not the best form of data, but you'd rather want to have it reduced in a form where it's easy to determine orientation. So we are building up our data pipelines, but this will be part of it. We will provide scattering data in a form that it's easier for you, more straightforward you to analyze it. Likewise, we fulfill the tomographic imaging. For example, you don't have much use of the raw radiographs. We will have data pipelines ready so that you actually get a 3D image that you can then work with. So much for data reduction, where we can help. Unfortunately, if one goes further into data analysis, such as quantitative image analysis, it is beyond what MAX4 in general, and in particular the ForMAX team has the capability of supporting. So let's say you have a 3D, a set of 3D images from tomography. You do that as a function of time, and you want to see how some structure in the sample evolves. It's not enough to have the 3D images or the 4D movie, but you also need to quantitatively analyze those images. And that can be, depending on your sample, very difficult and very challenging task. And unfortunately, the ForMAX team has very little spare time for helping you with that. We do have collaborations. MAX4 has for example, collaborating with a center in Denmark called KIM, Center for Quantification of Imaging Data from MAX4. that can help you with this kind of analysis. So I'd suggest have a look at their homepage and see what they can, how they could help if you don't have this expertise yourself. Okay, that leads to the end of my talk. I hope to see many of you at ForMAX in the not distant future. And yes, Sam and I are ready to take questions.
Thank you so much, Kim. Really great overview. Now we know much better how to apply, how to write the proposals. And I can already now see one comment from Emanuel Larsson in the Q&A. And I was wondering if Emanuel is here. Maybe you can even unmute yourself and join the discussion, because I think that's a good point that you made. I guess Kim and Samuel, you can see the comment in the Q&A, right? So basically what Emmanuel said, he said that there is also a commissioned REO, XREO, and it has a sample environment for performing tomography combined with rheology. And would it be something of interest for the ForMAX in the future? So, for instance, yeah, combining the environment, the sample environment and the REO SACs.
Mm-hmm.
I would say that's a question to the audience.
Mm-hmm.
So we have decided that the development of sample environments at ForMAX should be community driven. So where the research community sees a need, and there we can put in time and resources to develop sample environments. As a personal opinion, I would say yes, this sounds very interesting. I don't quite see how they manage it, but this should really be driven by the research community.
I agree with you, because it's such a time-consuming process to, you know, like set up everything and modify specifically for each experiment. But I think it somewhat will be also related to the work that soon will be presented by Roland Kadar. So all of you who are today with us, please already book in your calendars on November 7th at 13 o'clock. Roland Kadar from Chalmers, he will give a presentation which is actually dedicated to REO SACs. So you can listen to one of the examples how the beamline was used successfully, and he will also demonstrate the results. We will soon announce this webinar too, so you can also register for it.
Yes. And Manuel, we need to have a brief chat about how to do REO tomography.
Exactly. Emmanuel, please write to us, because I don't know, maybe I am allowing you to talk, but maybe you're busy and you can't talk. So please feel free to get back to Kim and Sam so you can discuss this in details. Are there any more questions from the audience? You can raise your hand, and you can also write in the Q&A and in the chat. I can say a little bit on behalf of my research group, or the group where I work. I work in the group of Professor Daniel Söderberg, and we have quite a few frequent users at the different beamlines. So far we mostly were going to DESI or doing the work in the States, but we are very much looking forward also to start working more on the user side, not only, you know, like on the management side as research team, but also as the researchers and scientists. So it's a very exciting process. And I think it's really great that you guys dedicate time to also help us with preparing of the applications and the proposals. I have a little bit of experience with it, and I know how careful you should be. And, you know, like not too much information, and at the same time, you should be on point. We had a great course by Stefan Ross from DESI. And as an assignment for the course completion, we had to practice to write the proposals to the DESI. So in my opinion, it looks like, you know, now what you offer for the next follow-up session that we will have on September 20th. That's somewhat, like an example of that exercise. So I really want to encourage the audience to make sure that you use this opportunity. And for the next meeting on the September 20th, you prepare a couple of slides and think about your ideas and thoughts and use this opportunity to discuss it with Kim and Sam to get some help with application, because the deadline for the beam time application is September 26th. So the time is quite tight. You need to be quick. So use this opportunity. I guess people can also, as you said, they can just contact you with the questions in advance, also not necessarily publicly during the seminar.
For sure. For sure. We're around and available to help. As I said, don't leave it to the last day, because the last days before deadline tend to be hectic. Yeah.
It's a lot of work. And then maybe also we should mention some of the news for the audience. So in the beginning of the next year, hopefully, fingers crossed, there will be the inauguration of the beamline. So, but for that one, we will see how it will be organized, and keep your eyes open. Follow the news on that research website and the newsletters and the LinkedIn also. We try to post there both MAX4 and also the research team. So we will see how it will be organized. So maybe we will have an opportunity to invite quite a number of interested researchers to attend and to see also the facilities, because it's a really exciting facilities. Oh, I wish we would be, like having this meeting now in real life, so we can ask the audience also who has experience with beam time. What were the challenges? But it's a little bit tricky in the webinar session. So maybe that's something like the format that we can also have for the next meeting on the 20th, so people can share their thoughts.
I agree. And I guess on a sort of closing note from our side, we've had a lot of talk about ForMAX the last 5 years. Now it's time to harvest. So I hope to see you at MAX4.
Yes, it would be really, really exciting. So it was a lot of work. A lot of work. I saw the construction sites in the beginning and then how everything evolved. So I'm wishing you the best of luck, because I know how much work it is for you as the specialist. Exactly like you said, sometimes just the measurement when everything is done and when everything is ready, it takes only a few seconds. But to prepare, to plan, and then to do data analysis, wow, you really need to love what you are doing and enjoy it, because it's a very time-demanding process.
Yes, but it's also fun.
But it's fun. You enjoy it apparently.
Yes, and good luck to everybody in the audience who are planning to submit a proposal. Looking forward to them.
Yes. Thank you so much, Sam and Kim. And I also want to thank Christine from that research team who helped with organization of these webinars. And what Christine will do, she will also try to edit the recording of this webinar, and it will be available on our YouTube channel. So you can watch it later. You can also share it with your colleagues and recommend them to watch and revise. And thank you so much for today, everyone, and all the audience. Thank you so much that you were with us.